Okay, chapter 4 is dimension reduction. Okay. So dimension here means how many variables, how many predictors there are in the data set. Okay. So if you have just one predictor, then it's one dimension. If you have two predictors, two dimensions, and so on. Okay. So the more the number of variables, the larger the dimension that we have. So it usually, it has to begin with. Data sets normally will have lots of columns of data, but as we prepare the data for analysis, we'll be adding more columns. Okay, for example, if you have factor column, then we will be defining dummy variables for that. So if you have a factor column with 15 possible values, that's going to spawn 14 more variables in place of one. And then there may be variables that you may want to transform, like in logarithmic transform or combination or exponential transform and so on. So those transformations and dummy variables is going to increase the dimensionality of the data even further. Okay. Then the larger the dimension, the more sparse the data space will become. Okay. For example, let's look at the sparseness of data set. Okay. So here we're looking at three different cases. Suppose we have just one predictor variable, okay, just one dimension. And suppose there are 8 possible values for that one variable, then even if you have only 4 observations, okay, 50% of the possible values are represented in the data. Okay. Now, if you add another variable, and for the sake of discussion, let's say that that also has only 8 possible values. Okay. Usually there will be many more possible values, but for our purpose, let's say there are only 8. So now we have 8 possible values for the first variable, and 8 possible values for the second variable. So there are totally 64 unique combinations, 8 times 8. So you get 64 combinations, and therefore to get the same 50%, okay, representation, now you need 32 observations. So if you have only 8 observations, then you can only take 8 observations, then you're not going to, that would be what? If you take 8 out of 64 is like less than about 15%. Now, if you go further down here, add a third variable. So now we have 8 times 8 times 8, 256 points. Now you need 128 observations to have the same level of representation like you started out with. So as you add more variables, the space, the data space, becomes larger and larger, and there is empty space. The empty space between points keeps increasing at exponential rate. Okay. So that, the larger the number of dimensions, more data we need to be able to have a truly representative data set. So that is the problem. So there is an incentive to keep the dimension low as possible. Okay. So that's the object of this chapter. How do you minimize dimension? How do you have a bunch of columns. Is there any way that there are some columns which we really don't need, we get rid of them? And of course, we don't want to get rid of columns that are useful to us. So we need to be careful about that. So that is the objective of this chapter, removing unnecessary data. So dimension should be reduced to only variables that have predictive value. Okay. Now, one possibility is what are the different approaches? Okay. remove or combine categories of factor variables. So you have a factor variable that has 50 different levels, which means you're going to have 49 dummy variables, right? What if you take those 50 different categories and combine similar categories and come up with just 20 categories instead of 50? So now you need only 19 dummy variables, not 49. So that is one approach, combining categories of factor variables. So that can reduce the dimension. And of course, it should be done with domain knowledge. You don't want to combine categories that are diametrically different. Okay. Now, review data summaries and remove redundant variables. So redundant variables are the ones that we already talked about, the variables that are closely related, like age and experience. Okay. This is especially the case when you have data coming from different sources and you have assembled the columns coming from various sources into your big data set. It is very likely that the same data column comes from two different sources and they are sitting here. The exact same column may be in a different name. Okay. So we should be able to identify variables that are redundant. Okay. Again, we're going to look at how to do that. Okay. Columns that are redundant, so we can throw one of them. We're not going to throw both of them out. You know, if you have two redundant columns, you keep one, you remove the redundancy. Okay, get rid of the redundancy. So that's one thing we need to do by looking at the summaries and reviewing the correlations among the predictors. We already did in chapter 3, we did a heat map. Okay, now we're going to look at a numerical method to identify exact combinations, exact pairs of variables that have high correlation. Okay. So if feasible, convert ordinal variables into numerical variables. Okay. Suppose if you have, say, number of people in a household. So you have 1, 2, 3, 4, 5, 6. So this is a categorical variable, but it is an ordinal variable. Okay. If you keep them as categorical variables, then you'll end up defining dummy variables for that, right? So instead, okay, if you have only few values for the ordinal variable, it makes sense to just leave it as it is and develop dummy variables. But if you have lots of values for the ordinal variable, then it may be okay to convert them into a numerical variable, so you don't need dummy variables. So that way, again, you can reduce the number of additional dimensions that you'll end up creating. Okay. So if feasible, convert ordinal variables. And then we're going to, at the end of this chapter, we're going to look at a procedure called principal component analysis. The principal component analysis takes a huge data set and then tries to condense it without losing the predictive value of all those predictors. Retain the predictive values, but reduce the number of variables that you need. And in this process, of course, this is not a costless process. You're going to lose something, right? So we will discuss that. What are we going to lose and what are we gaining and how to do it? Okay, so that's our principal component analysis. So apply data reduction technique called PCA, principal component analysis. Okay, and then we can also use stepwise regression. Okay, in your statistics class, I hope it was covered and you vaguely remember from the past. Stepwise regression is a method that can select variables that are important, that have predictive value, and leave the variables that do not have predictive capability. So that's another method that we can use to remove redundant variables. Cursive dimensionality, we just discussed that. Okay, adding variables increases data space exponentially. So we need to reduce with minimum sacrifice in accuracy. The process of dimension reduction is referred to as factor selection or feature extraction. Feature is again another terminology used for predictor variables. Or factor selection is again variable selection. These are just terminologies. Okay. So that's the overall summary of what we're going to do. So we will do the actual work next time. And by the way, next week I'm going to be out of town for a conference. Okay, I'm going to prepare videos for you to watch and work. So in place of attendance, you need to submit the classwork as an RMD file. Okay, and that will count for attendance for Tuesday and Thursday. Okay, so I'll have the videos posted before I leave. So I'll be preparing that over the weekend, and I have them available. So we should cover chapter 4. The rest of chapter 4 we'll cover for next week. Okay. So any questions? All right. So I'll see you not next week, in the week after that. Yes. Okay, let me close that.